Maybe let's start. So let me just recall what we were talking about in the previous lecture towards the end of it, and then we'll continue. We define vector spaces and define some sort of basic notions of linear independence or dependence, just to capture whether in some sense we have redundancy or not. And then we define the span of a set as the set of all finite linear combinations I can form using vectors from the set. So and one thing which probably I didn't mention last time, but is easy to check, that first of all, the span of S is a subset of the vector space, because scalar multiplication and addition of vectors still keeps you in the subspace. And we started with all these vectors v1 to vn from S, which are also in V. And moreover, this is a vector space itself. So so you can check that if you add two things from the span of S, you stay inside the span of S. And if you multiply something in span of S by a scalar, you stay inside the span of S. So by subspace, I mean, first of all, it's a subset. And is a vector space under the same notions of addition and scalar multiplication. So and this is also kind of a useful property, and in the general definition of subspaces, something we will refer to fairly often. We also defined what a basis is. It's in some sense a set which is linearly independent and captures all the information we want about vectors, in the sense that the span of B is everything. So it's the entire vector space. So if you look at linear combinations from B, you get the entire vector space B. And we also looked at an alternate characterization, or I sort of proved half of it, is that B is a basis if and only if it's a maximal linearly independent set, in the sense that it is linearly independent, but if you add any vector which was not already in it, it becomes linearly dependent. Okay. So, and this sort of also captured the notion that there is some sort of kind of limit to how much linear independence we can have. For example, and this was also an example proposed for, let's say, just R2. Any questions about these before we continue? This is just a recap of where we were last time. Okay. And we sort of started talking about this convenient tool called the sinus exchange principle, which lets us prove a few useful properties of vector spaces. And by itself, the statement is just, if you have a bunch of linearly independent vectors which live inside the span of another collection of vectors W1 to Wn, let's say, then you can remove whatever vector you want from the original set from the V's. You can remove any Vi and replace it by an appropriate Wj. So you can remove whichever vector Vi you want, and there is always a Wj you can put back in, such that the new collection is linearly independent. And in some sense, you didn't cheat. So if Wj was already kind of one of the vectors you had after removing Vi, then the fact that you take the union is meaningless. It doesn't really change the set. So not just that, there is some sort of interesting vector wj that you can put back. So okay. And the new set is still linearly independent. All right. And I kind of alluded to a few interesting consequences this had, but let's maybe prove it before. Okay. Any questions about the statement? All right. So as before, we'll sort of try to prove it by a contradiction. So let's say this is not the case. Okay. So suppose not. Then so we need to take a negation of the statement that for all I there exists j, right? And the negation is just that there is at least one I for which it fails. So there is at least one I such that no matter what wj you try to put back, you get linear dependence. So so yeah, let me skip one step and say that okay. So we saw that when you have linear dependence, you can say that there is at least one vector which can be written as a linear combination of the others. So this is an equivalent way of phrasing linear dependence. And here, the only vector for which this can happen is wj, because v1 to vk were linearly independent. So in the set of v's, you will not have that one of the vectors is a linear combination of the others, or at least the coefficient of wj will be non-zero in a linear dependence. In any linear combination which sums up to zero, it cannot be only formed of the v's. There has to be at least this wj in it. And so we can write wj as a linear combination of the others. Okay. And notice that now I kind of dropped the condition that wj is sort of not in already present, because this applies in both cases. So if wj is already present, it's still in the span. And otherwise, because our assumption or sort of because we are assuming the claim is false, it's still in the span. So in either case, we can say that wj is just in the span of v1 to vk minus vi. Okay. So this is an implication if we assume that the claim is not true. Okay. Is that okay? I just basically skipped a step. Okay, but this is interesting because we just said that every wj is in the span of v1 to vk minus vi. That means that the span of all the wj's is a subset of right. So if all the w's lies in the span, then all linear combinations of w's can also be written as linear combinations of the v's, even sort of removing vi. And so the span of all the w's also lies in this span. But now there is a problem because we assumed all the v's lie inside the span of the w's. So in particular, vi lies in the span of the others. And that's a problem, because now we get that V1 to Vk are linearly dependent. That contradicts what we were told. We were told that V1 to Vk are linearly independent. And we said that if we assume that the claim is false, then V1 to Vk are linearly dependent. So our assumption is wrong, and the claim has to be true. Okay. Any questions for this proof?
Really quickly, this isn't about the proof, but I wanted to ask if you wanted to start the recording.
Oh, isn't the recording already in progress today? It's
Oh, my bad, my bad.
Yeah, sorry, I did forget it last time, and but I tried not to stop it this time. So, okay. But thanks for the reminder. Yeah, please do. Yeah, as I demonstrated last time, I'm perhaps not very reliable on that part. So if you can catch me, that'll be great. So, okay. Any other questions or comments? All right, and then we can actually quickly deduce the corollaries we alluded to last time. This principle itself has a few interesting consequences. The first one is that if you have two bases, let's say V1 to Vk and W1 to Wn, notice that because I'm writing the basis as V1 to Vk and W1 to Wn, I'm kind of assuming that it's a finite set. This may not always be true. You might not have a finite set which is a basis, but here, I mean, I am writing it out as V1 to Vk with some finite k and V1 to Vn with some finite n. So I'm saying that these two are finite bases. Then k is equal to n. And as you will see, yeah, I mean, okay, we'll slowly see more consequences. Okay. So in particular, any two bases, any two finite bases have the same size. Okay. And the proof is just kind of applying what we saw on the previous slide. So basically, you repeatedly so you remove one of the VIs and add a WJ. And but then, because of what we said, you have to add a new W every time. You can't add a W which you already added before, because we have this condition that what you are adding is something different from what you added before. Okay. And actually, this will tell you that the span doesn't change. But you added a new W every time, and you removed a V. You can only you're going to remove all of the V's. There are k of them, and you can keep doing this according to the Steinitz exchange principle. But then you have to have at least k of the W's to be able to do this. If the number of W's was less than k, then you won't have a new W after a while. Right? So we need which gives us this n is at least as large as k. But then there was nothing special about doing this argument with kind of B1 and adding things from B2. You could also have done the argument in reverse and started with B2 and added things from B1. B1 is linearly independent and B2 is linearly independent. And we have the conditions that, so for this half of the argument, we use the fact that B1 is linearly independent and B1 is in the span of B2. This is what we use to run the argument in the forward direction. But because both are bases, the opposite is also true. B2 is linearly independent and B2 is in the span of B1. So you apply the Steinitz exchange principle with kind of the reverse and replace one of the W's and keep adding a V every time. Again, you need enough V's to be able to add, and this will give us that K is greater than or equal to N. And just combine the two, that tells us that K is equal to N. Does that make sense? All right, so that's one application. There are other applications which, so let's just maybe have a definition which captures what we are saying, that there is a finite basis. And so in general, a vector space is called finitely generated if it can be written as a span of some finite set. In particular, this set can be the basis, but it doesn't have to be. Okay? And then we call this kind of a set a generating set. So T is a generating set if V is equal to span of T. In particular, any basis is a generating set, and in some sense, a generating set kind of always has at least as much redundancy as a basis. So again, using the Steinitz exchange principle, you can prove that a finitely generated any finitely generated V, sort of something which has a finite generating set, will have a basis which is a subspace of the generating set. Okay. Let's see. Okay, and another nice consequence of this is that if you have, again, a finitely generated vector space, then you can start with any linearly independent set and find a basis which contains this linearly independent set. So in some sense, you can kind of get bases from both directions. If you're given a generating set, you can find a basis which is a subset of it. So don't need any new vectors once you have a generating set. If you are given a linearly independent set, then you can always find a basis which contains it. So you can reduce or sort of prune out a generating set to a basis. You can extend the linearly independent set to a basis. So any kind of so basis needs to have two properties. One, it's linearly independent. The second, is that the span is equal to the entire space. And if I give you a set with only one of these properties, you can get something with both. Okay. So the first is a generating set where the span is the whole space. You can make it independent, or you can find a subset which is. Second is an independent set, and you can find something which has the entire space. And all of these are again applications of the Steinitz exchange principle. So okay. Any questions about these? So these are sort of exercises to try out. Any questions? All right. So what did we learn so far? We said that finitely generated vector spaces have at least one basis because they come with a finite generating set, and we can always find a basis which is a subset of this generating set. So we are sure that there is at least one basis we will get. And if someone gives you two bases, then they will have the same size. So in some sense, the size of a basis is an inherent property of the vector space. It doesn't really depend on the basis. And this is sometimes referred to as the dimension of the vector space. And because a finitely generated vector space will have a basis which is of finite size, sometimes we also call these as finite dimensional vector spaces. Okay. So an alternate term you will see is okay. And finally, one other interesting consequence, which was also pointed out in one of the examples earlier, that if you have any linearly independent set with the right size, then it's a basis for the vector space. So if you have any set with the size of the set is equal to the dimension of the vector space, then it's going to be a basis. So you just need to find a linearly independent set with the right size, and you're done. Again, you can prove this as a consequence of what we discussed so far, or a consequence of, I mean, here it's, yeah, because if you have a linearly independent set, you can always complete it to a basis. So you can always find a basis which contains it. And if you completed it to something which was bigger than S, then you have a basis whose size is larger than the dimension. That can't happen. So the completion is just S itself. There is no interesting thing you need to do to extend it. You're already at the level where you have a basis. Okay. Any questions? Okay, so these are all cases about, let's say, finitely generated vector spaces. You can reasonably ask, what happens if the vector space is not finitely generated? So maybe there is no finite generating set which gives the entire vector space. By the way, can anyone give me an example of a vector space which is not finitely generated or may not be finitely generated? I claim that we've already seen multiple examples. Something in the chat. Okay. Polynomials, real numbers, etc. Okay, so there are multiple examples. So over the field R, or maybe real numbers over the field of rational numbers. Okay, how do we prove that the polynomials are not finitely generated? I mean, it's true, but okay, so here, let's go back to what we said about, okay, maybe someone already suggested a solution in the chat. Okay, great. So, yeah. So you can prove it by contradiction in the sense that suppose they are finitely generated. So suppose I give you a list of some finite number of polynomials, say 20 of them that generate the entire vector space. Then go look at these polynomials and see what is the highest degree term you see. There are 20 polynomials. You can look at the degrees of x in each of them, and maybe 100 is the highest degree you see. Okay. But then what about x to the 101? It's not going to be a linear combination of these polynomials because linear combinations can never increase degree. So if you give me any finite set, I can at least tell you one polynomial that is not in the span of it. Because, I mean, for any finite set, I can go find the maximum degree of anything that appears to me. Okay. Right. So, and so, okay, this is, implies that at least there is no finite generating set. It also tells us that there is no finite basis. Is there a basis at all? Now, it kind of gets interesting because usually when we think of polynomials, we're used to thinking of the basis as the monomials, let's say 1, x, x squared, x cubed, and so on. Okay. Yeah, so this this is a basis in the sense any polynomial you want can be written as a finite linear combination. For reals over rationals, it's a little less clear. And one thing to kind of distinguish now, which is important here, is that we defined a span using only finite linear combinations. Because in an abstract vector space, we don't know how to define infinite sums, because for infinite sums, we need notions of distance, convergence, etc. And a generic vector space may not necessarily have notions of distance and convergence. So, for example, go back to finite fields or some of the other examples we saw. So we may not always be able to define what it means for a sum to converge or for a series to converge. And so we only restrict ourselves in a generic vector space, at least, to talking about finite linear combinations. And now, if you think of, for example, reals And is there an infinite set of, possibly infinite set of rationals so that you can write every real number as a finite linear combination out of it? It's less obvious. So, I mean, we know that for rationals, we can write maybe converging sequences of, or sorry, for reals, we can write maybe converging sequences of rationals which converge to this number at least. But here we are not allowed to do that. And in general, I mean, it is true for any vector space that you can find a basis. The basis may be infinite, but every element of the vector space will be written as a finite linear combination of the basis elements. And such a basis is called a Hamel basis, where you're only allowed finite linear combinations. This is to distinguish it from something called the Hilbert basis. When you have notions of distance, etc., you can take infinite linear combinations, and sometimes those bases are easier to find. But the existence of a Hamel basis requires the axiom of choice, or equivalently Zorn's lemma, which basically uses the definition of basis we had as a maximal linearly independent set. And Zorn's lemma kind of says that under some conditions, you can always find a maximal linearly independent set, and some conditions which you can prove for a vector space. Okay, so, and I'll include a proof in the notes, although, yeah, I mean, we won't necessarily discuss it in the lecture because it requires defining few notions which may not be as relevant for the rest of the things we want to discuss. But I will include it in the notes, and it's a good thing to know, definitely. Okay. Any questions? All right, so now that we have at least a couple of notions in vector space, basis, span, and so on, we can go to our first application, or at least use this to prove something interesting. So, application is sort of what's called the Lagrange interpolation formula, or Lagrange interpolation rule, or whatever. The goal is to find a polynomial which fits, or sort of, maybe you can think of it as a curve, y equals p of x, which fits n data points. So let's say you are given the sort of n points on the curve. So p of maybe at x equals a1, the value is b1. At x equals a2, the value is b2, and so on. So you can think of these as n points on the curve. And the goal is to find a curve. So equivalently, you can think of finding a polynomial curve y equals p of x, which fits this data. And Lagrange interpolation tells us that there is a curve of degree, or a polynomial of degree at most n-1, which fits this data. And moreover, this is actually unique. So if you are given n points on this curve, and this is a generalization of a fact which we have already seen, that if I give you 2 points, you can draw a unique line through them. If I give you 2 distinct points, and if I give you 3 points, you can draw a quadratic curve through them, and so on. And this is just a degree n generalization of this fact. Any questions about this statement? All right. So, first of all, it's okay. Let's proceed. So, first of all, it's kind of easy to see that if you find a polynomial, it will be unique, because a polynomial of degree n-1 can have at most n-1 roots. And if you found p1 and p2, then p1 minus p2 will be 0 for all points a1 to an, if p1 and p2 fit the above data. Right. So if you found two distinct polynomials, then the difference will also be a degree n-1 polynomial with at least n roots, which is a problem. Okay, then it can be only the identically zero polynomial, and so P1 will be equal to P2. All right, and this is it's a fact which we kind of know, but we can also prove. And we can also see we can write it from Lagrange interpolation also. So I'm claiming that you can find a polynomial of degree n-1. Let's just go back to this vector space of degree polynomials of degree at most n-1. I claimed that it's a vector space in the previous lecture, and because it's a subset of the space of all polynomials, it's actually a subspace. And let's try to understand some things about it. What's the dimension of this subspace? Is it even finitely generated? Okay. Dimension is n. Because you can think of 1x, x squared, x to the n-1 as a basis. So these are all linearly independent. You cannot write a power of x as a linear combination of other powers of x. And it's as polynomials, and then it's a basis because every polynomial can be written as a linear combination of these terms of the polynomial degrees at most n-1, and all bases have to have the same size. This is a size n. Okay. Now, once we know this, we can use a property we proved last time, which is finding a different basis. So if you remember, we talked about these polynomials that you have n distinct points, and you look at the polynomial fi, which is the product of x minus aj's for all j which is not equal to I. So, and we proved last time that these are linearly independent polynomials or linearly independent vectors in this vector space. Okay. And the degree of each of them is at most n-1. So, and based on what we just saw, any set of linearly independent vectors of the right size is a basis. So these must also be a basis. So I just gave you n linearly independent vectors in an n-dimensional space. They must form a basis. Because they are a basis, any polynomial p that we are interested in must lie in their span. And in fact, you can check that so actually Lagrange interpolation can also be used to prove the fact that any sort of polynomial of degree n-1 has at most n-1 roots, using the fact that if you have a basis, then any vector can be written as a linear combination of the basis elements and a unique linear combination of the basis elements. Because if you had two linear combinations of the basis elements which gave you the same vector, then you can subtract one from the other and you get a linear dependency between basis elements. So this is just true for any basis, in particular this basis. Which cannot happen unless all coefficients are 0 because of linear independence of basis elements. Okay, good. So that's a sanity check. So for every polynomial, there must be a unique linear combination. And now, I claim that we can find these coefficients very easily based on what we know about the data. So Suppose we want to find this polynomial which takes value bi at point ai. Okay. So plug in ai on both sides. Just using a different index. And because of the form of these polynomials, everything except the ith polynomial is 0 on point ai. This is also what we use to prove that linearly independence. Right? So they contain it as a factor. So there is only one term which survives in the summation, and it's equal to f of ai. And we know from the data that p of ai is equal to bi. That's the kind of data we are trying to fit. So that tells us the coefficient exactly. It's bi divided by f of ai. And we get that the unique polynomial which fits our data is sum over I, bi divided by f of ai, sorry, fi, times phi of x. Okay. So, I mean, you can expand out these FIs and write them explicitly. And this is a formula for fitting any endpoints to a degree n-1 curve. This is called Lagrange interpolation. And you can also check that this implies the fact that a polynomial of degree n-1 will have at most n-1 roots if it's a non-zero polynomial, just because if it didn't, you can think of these roots as the data points. So think of trying to find a polynomial which is 0 at n points. All the b's are 0 and all the ai's are distinct. No, b's need not be distinct, just the a's. That's what we needed for linear independence. And if you plug that into Lagrange interpolation, you will get all the bi's. Because they're 0, you will just get the 0 polynomial. And because these fi's were a basis, this is the unique polynomial which does this. So this actually can be used to prove that a polynomial of degree n-1 has at most n-1 roots, a non-trivial polynomial. Okay. And so this is what we use for a sanity check. It's a fact we know, but this implies a proof. And moreover, you can check that we didn't really use anything about real numbers in this entire proof. So you could have polynomials with coefficients in any field. The only thing we needed about these fields that we had n distinct data points. So the field should have at least n elements. But once you do, this entire calculation just use definitions of basis and linear independence and the fact that we can divide by things like f of ai, etc., fi of ai. And these are all operations you can do in a field. So that's a good exercise to go back and check. And this is used in a variety of applications, for example, in decoding of certain error correcting codes defined with polynomials, in particular things called Reed-Solomon codes, Reed-Muller codes, etc. It also has a very sort of cute application. So this is, I guess, an application of an application in cryptography, which is called secret sharing. So it's a scheme due to Shamir. And the idea is, suppose you want to share a secret in a distributed way. So this can be some sort of key for decryption, or it can be a password, or it can be the kind of example given sort of the joke story is some sort of nuclear codes which are shared between generals, and probably a more sort of ominous sounding example. But what you want is that it's distributed in a way that if any d of these people get together out of n people, then they can learn the secret. And if less than d people get together, they know nothing. So they don't really learn anything about the secret. So it's a secret which requires at least a certain number of people to be present for them to learn anything about it. And the scheme is just based on Lagrange interpolation, or what we learned about polynomials. That and you choose a field, and here a finite field, because real numbers with arbitrary precision you can't send to people. They just require infinite number of bits to write down. So choose a finite field which is large enough. It has at least n+1 points, also if it is greater than n points. And also, let's say your secret you can think of as some number. You can write it out in binary, etc. So you can think of it as some possibly large number, and then choose a field which is at least or somewhat bigger than the size of this secret. Okay, and we'll discuss more in kind of in the probability part of the course, but just pick coefficients of a polynomial of a degree d-1 polynomial at random, everything except the 0th coefficient or the coefficient of x to the 0, which you take to be your secret. Okay, and then you just distribute values of these polynomials at different points from 1 to n, not at 0, and the secret s is actually the value of the polynomial at the point 0, right? Just because of the way we designed the polynomial. So now these n people know the value of this polynomial at n points. The degree of the polynomial is at most d-1. None of them knows the value at the point 0, which is the hidden secret. Any questions about the scheme? Well, I claim that it does whatever we want. So any d people can find the secret, because if d of them get together, they will they have d data points or d distinct points, and they know the value of a degree d-1 polynomial at d distinct points. So they can actually find the entire polynomial by Lagrange interpolation. And then they can just compute the value at point 0 once they know the polynomial. And if d-1 people get together, and yeah, again, we can make this precise with some more knowledge of probability, but if d-1 people get together, then intuitively, or I mean, you can check that, let's say we have the person I1 who knows the value at point Q of, who knows the value at point I1 and so on. And let's say we have d-1 of these. And now I claim that the knowledge they have is consistent with any value of the secret I want. Okay. So now think of me adding a data point, which is 0 and s prime for any s prime. Okay. There is a unique polynomial consistent with this because I'm giving you the value of a degree d-1 polynomial at d-1 points. So for any value of the secret, there is a unique polynomial consistent. And if you sort of want to calculate probabilities, you can go back and check that given what they know, the probability of the secret being s prime is the same for every value of s prime. So they learned nothing. I mean, they could have just sat down and just guessed the secret randomly, and that's equivalent to any exercise they can do with Lagrange interpolation. So, or in fact, information theoretically, just given what they know, they don't learn anything about s prime. It's just as good as guessing randomly. Okay. So that's one, and then simple application, and all we needed is Lagrange interpolation. We did use it over a finite field, which was large enough, and this is something you should maybe go back and to the proof and check that it still works. Okay. Any questions? Okay. So we learned a little bit about vector spaces and how to think of bases of vector spaces, etc. The next thing I want to talk about is objects which do something to vector spaces. So in some sense, so far we were thinking of vector spaces as static objects, kind of sitting there. We are trying to see how to describe them, how to write one thing in terms of another thing, etc. And now it becomes a little more interesting once you can actually have something which acts on a vector space, modifies it in some way. And these are things called, or the interesting objects we'll look at are what are called linear transformations. So for this, we'll need two vector spaces. Let's say V and W, and both of them, importantly, are vector spaces over the same field. Now, we will say a map phi from V to W is a linear transformation. It kind of, if it acts on these vectors in a way that is kind of consistent with linear combinations or operations which we do on vector spaces. And a few things to notice. Again, there is a little bit of an overload on notation here. So here, if I add two vectors, the input vectors, according to the notion of addition in the vector space V, then I get, or I add them later after applying the linear transformation according to addition in the vector space W, I get the same result. Secondly, again, same for scalar multiplication. Note that the scalar C did not change, and that's why we needed that we have the same field. You can multiply by C either inside of vectors of V or vectors of W. For both, you should be able to do this. Okay. And you can check that this implies an interesting property that the linear transformation evaluated at point 0. Again, this is a bit of an overload in terms of notation. The 0 of the vector space V is equal to the 0 of the vector space W. Okay. And an example which we might have seen many times is a matrix. You can think of a matrix, and we will usually think of vectors as column vectors in the course. So you can think of the matrix A as kind of multiplying a vector V. And it gives you some other vector. And the number of entries in V is equal to the number of columns of this matrix. So you can think of it as defining a linear transformation from Rn to Rm. And all these properties of linearity just follow from what we know about matrix vector multiplication. Any questions about that before we proceed? Just the definition of linear transformation in an example. Okay, so now let's check a few other examples which may not quite look that way. And I mean, let's also see if they define proper linear transformations or not. So recall, we defined this sort of C with some domain and some range as the space of continuous functions. And so let's say we think of continuous functions which take inputs in 0, 1, and maybe map them to space of continuous functions which take inputs in 0 to 2. The first one is a map which, so remember, phi is acting on functions. So here it sort of eats a function, which is a continuous function, and gives you a new function. If we call this G, then when phi acts on F, it gives us the function G. And we are just defining the function G by telling you what it is equal to at every point. To compute the value of G at any point X, you go back to F and compute it at point X over 2. So now you can use the range 0 to 2 to compute it. And I claim that this is a linear transformation. Again, so you can check that phi of F1 plus F2 is phi of F1 plus phi of F2. And if we multiplied our input function by some constant, then we'll get this. Okay, what about the next one? So now to compute the value of phi of f at x, I actually look at f at x square. Is this a linear transformation? Guesses, arguments, counterexamples? Feel free to also unmute yourself and speak if you prefer. Okay, so one answer is that addition does not work, so it's not a linear transformation. Okay, so actually it is a linear transformation because we need to check what is the object we are adding. So phi acts on functions, and so let's check what happens when we try to add two functions. So we say, suppose I want to compute phi of f1 plus f2. What is this? This is a function whose value at x will be equal to the value of f1 plus f2 at x squared. But the value of f1 plus f2 at x squared is equal to the value of f1 at x squared plus the value of f2 at x squared. And the value of f1 at x squared is the value of phi of f1 at point x plus the value of phi of f2 at point x. So we do have that phi of f1 plus f2 at every point is equal to phi of f1 plus phi of f2 at that point. So we do have addition the way we want it for functions. It kind of looks nonlinear because it's nonlinear in the input of the function, but we don't actually care about that. It has to be linear in its action on the function. The function itself does some weird nonlinear things to its input, doesn't matter. Okay, so it's kind of useful example to keep in mind because it really looks nonlinear, but it's really just the function where we care about linearity. Okay, the same you can check is true for scaling by a constant. Because you will scale the values of the function, not the input. Any questions? Or maybe comments in chat? Excellent. So there is a comment that if we try to define, so maybe that's an example I should give next time, is if we define phi of f at x is equal to f of x whole square, this will not be linear. Because this is not acting linearly on the value of f, which is, and then that's a problem. Okay, but if it's doing something nonlinear to the input, it's not such a big issue. Okay, another couple of nice examples to check. An operation on the Fibonacci space, which if you think of it as a sequence written down one value for every number 0, 1, 2, 3, and a function which kind of shifts, or an operator which shifts this left by one position. So the new value at position n is actually the old value at position n plus 1. Or the derivative operator. So you can take a polynomial, differentiate it, you get another polynomial, and you can check that all these are also linear transformations. Okay. So it's just to keep in mind, I mean, there is some equivalence between linear transformations and matrices, at least for finite dimensional vector spaces. You can always write linear transformations as matrices. But even in these examples, it may not be always the most convenient way of thinking about linear transformation. So it's sometimes useful to also keep this abstract notion in mind, that it's just a map and you just observe what it does to every vector, rather than trying to think of it always as a matrix. Although, yeah, in finite dimensional vector spaces, you can. Okay. And here is another sort of statement which solidifies what we just said about specifying linear transformations as matrices in finite dimensional vector spaces and more generally. So basically, you can specify a linear transformation completely by just telling me what it does to a basis. And in some sense, when you think of writing it as a matrix, what you are saying is that the columns of the matrix will tell you what it does to some kind of standard basis for the space. Okay. And more generally, you can specify it in terms of pick any basis, pick any values whatsoever, no linearity constraints, nothing on that basis, because in basis, there are no linear relations between elements of the basis. They're all independent. So you can do pretty much whatever you want there. And once you give me these values, you specified the linear transformation completely. So there is a unique linear transformation which is consistent with what you just told me about the basis. So for the basis B, what alpha does to this basis, if the linear transformation has to be consistent with it, there is a unique one. Okay. All right. So, and again, the proof is mostly just following the definition of a basis. So, for so we'll need to prove two things. One, there exists at least one linear transformation, and secondly, it's unique, so there is no choice in terms of. So let's define the linear transformation to be equal to alpha on all elements of the basis. So here, because we need to satisfy this condition, so let's just say that we will. And now, in some sense, our hand is forced. So there is not much else we can do. So let's say if we have any vector v, which is in the vector space, but not in the basis, there exist, and as we said before, unique coefficients and vectors in the basis such that you can write this vector v as a linear combination of the basis elements. Okay. But if there is this unique representation, then there is not much we can do in terms of phi, because this actually tells us what we must be on this vector v. It should be equal to because on the basis we just defined it to be equal to alpha. So alternatively, you can say that, okay, let me define this linear transformation, which at any point v writes it uniquely in terms of the basis, computes the values of alpha at the basis points, and computes the value of phi accordingly. And this is the unique transformation because anything has to satisfy this property. Okay. Any questions before we proceed? I claim that this is enough information to maybe go and solve the first puzzle, which is in terms of, I mean, it's still non-trivial, but it's can be solved just based on linear transformations and vector spaces. So yeah, you can go think about it if you want. Yeah, so it's convenient to think of linear transformations in what it in terms of what it does to a basis, and sometimes the choice of basis might impact how easy it is to think about something, and then we will kind of develop on this idea much more later. Now let's go to two interesting objects that are defined in terms of linear transformation. So if you have a transformation v to w, its kernel is defined as the set of all points where it just returns 0. So where it acts in perhaps not so interesting a manner. And the image is whatever interesting information it does give us. So it's the set of all points now in W. So notice that these live in W and these live in V. So these are sort of sets in different vector spaces. And in fact, they are both subspaces. So and this is something I'll ask you to check as an exercise. So the kernel and image are subspaces which are defined in different vector spaces. And they capture, in some sense, what is the set of points where phi does not act in an interesting manner. And on the other hand, what does it give us when it does act in an interesting manner, which is the set of images. Well, okay, we include 0 in the image of phi, so it's the point 0 is also part of it. And before we proceed, let's just check a quick exercise. So again, as we said earlier, we can use a matrix to define a linear transformation. Let's say we look at this matrix. Any guesses as to what the image of this matrix is, or the kernel, or the image on the kernel of the appropriate linear transformation? Okay. Right, so the image is all of R2. And this is maybe, sort of, let me remind you of a useful way to think about matrix vector multiplication, that if you have a matrix A with columns, let's say A1, in this case A2, and A3, which are column vectors, and you multiply a vector, let's say x1, x2, x3, then it's just taking the linear combination of the columns. And so the dimension of the image is just asking what is the space spanned by the columns, or the image is nothing but the span of the columns. Okay. And in this case, the columns already include a basis for R2, for the set of all real vectors with 2 coordinates. So the span of the columns will be everything. So that tells us that the image that is R2. What about the kernel? Okay, sorry. Right, so the kernel is the span of a one-dimensional vector, and with entries 2, -1, 1. It is a, oh, sorry, 2, 1, -1. Okay, and so it's this kind of one-dimensional space, or the space with a basis with one element. And again, you can check this by doing the linear combination that we wrote down. But the interesting thing I wanted to point out is that the image is 2-dimensional and the kernel is 1-dimensional. And this is something that happens in general. So our matrix acts on 3-dimensional space, and the image and the kernel add up to, or the dimensions of the image and the kernel add up to 3. And this is something which is called the rank nullity theorem. So the dimension of the image is also referred to as the rank of the linear transformation, and the dimension of the kernel is also referred to as the nullity of the linear transformation. And it's always true that the rank and nullity, at least when you start with a finite dimensional V, so that the addition makes sense, is equal to the dimension of V. Is the statement of the theorem clear? Okay, and the proof is actually an application of what we did so far. So let's say the dimension of the kernel, or the nullity, was k. Okay, so some finite number k. It's a subspace of the finite dimensional space V, so it's going to be some finite number. It's not going to be, the kernel of V cannot be infinite dimensional. And if it was, let's say, V1 to Vk, we can complete it to a basis assuming the dimension of this space V is, say, okay. So we can always complete it to a basis. Now I claim that we have enough information to prove that the rank is n minus k, which is what we would need. Okay. Any suggestions on to prove it? Any guesses? So here we can actually prove it by explicitly giving a basis for the image. So my claim is that if you look at the vectors that you needed to add to complete the basis, they form a basis for the image. Of course, when you apply phi to the first k vectors, you just get 0. So you should never include 0 in a basis, because a basis should have linearly independent vectors, and 0 is not linearly independent. Even it's a one set with one element with linear dependencies. Okay. And the rest I claim is, first of all, they are linearly independent, and they span all of the image of phi. Okay. So I need to prove two properties about it. First, let's prove that it's linearly independent. So if not, then there is some linear combination of these vectors, which is 0. But because of the linearity properties, this tells me that if I instead took a linear combination of the V's and then applied phi to it, I will get 0, which will mean that this is in the kernel, which indeed it will mean that I can write it as a linear combination of the basis of the kernel vectors. So I can write this vector as a linear combination of the kernel vectors which is a problem because all these vectors were linearly independent. They're not supposed to have any linear relationships between them. You can't write a linear dependency between them. So this can't happen. So these are linearly independent vectors, which is already enough to say that the dimension of this image is at least n minus k, because I already exhibited n minus k linearly independent vectors. And these are actually also sufficient to capture the entire thing. So that we can check, because any vector w in the image can be written as phi acting on some element of v. And because we have a complete basis for v, we can write down any vector v in terms of these vi's from 1 to n. And again, when we split it by linearity, you get the first k plus the rest. And these are all 0. So what we are left with is a linear combination of the remaining n minus k, which is what we wanted. So it's a basis. Any vector in the image can be written in terms of these vectors, and there is sufficiently, and they're linearly independent. That's all we needed to prove. Okay. Now, before we break, let me just point out one more interesting matrix. This time, let's think of it as acting on column vectors with entries from the field F2. So just a very small field with 0 and 1 modulo 2, addition, multiplication modulo 2. And let me ask you to check the dimension and kernel for the linear transformation defined by this matrix. And okay, so first, what's the dimension of the image? Or rather, you can even answer what is the image. It's again, the image is a set of linear combinations of all the columns. What all can you generate by taking linear combinations of all these columns? Right. So the answer is everything. So you can generate all of F2 to the 3 because you have 3 linearly independent vectors. And because the image is a subset of the range, or F2 to the 3, that's as large as the dimension can be. So the dimension of the image is this. That tells us the dimension of the kernel is 4, because they have to add up to 7. Okay. So the kernel of this is a 4-dimensional subspace of F2 to the 7. And it's an interesting exercise. Think about it, and we can probably discuss it in the next lecture. It's actually a code in the sense that if I give you a 7-bit vector and I specify one of the bits incorrectly, I just change it, you can figure out what I changed and you can correct it yourself. So it's something called the Hamming code. can be generalized to k-bit strings. And in general, a lot of interesting codes are specified as kernels of linear transformation. There's a more general class of codes called LDPC codes or low density parity check codes, which are a parity check is nothing but saying sort of a matrix vector multiplication. And they are usually specified as kernels of some matrices with each row having relatively few non-zero entries. Okay. So there is sort of a nice connection between linear transformations, kernels, and a class of interesting codes, and not just over F2, but over the more general finite fields. Okay. So, okay, this example you can think about more, and maybe if you figure out how this is a code, then you can also think about what's the k-bit generalization of it. And then we'll pick up from here in the next lecture. Any questions?